afraid. Just as long, just as long, just as long as you stand by me. Now, darling, darling, whenever you're in trouble, darling, won't you stand? I need just a little heaven here right now. And darling, darling, won't you stand by me?
All right, Unit 5.06, we're going to interpret the parameters of a function in terms of the context of the situation. There should be the situation that the function models. So when I say parameters, what am I talking about? Well, when we look at an exponential function, so for example, f of x equals a times b to the x, the parameters are the values that a and b are. And as we've talked about a good amount, depending on what b is, that really changes how our function is going to operate. And so we can actually answer a lot of questions, and you've been doing so already, just by thinking about what your b value is. And there's also going to be a way, obviously, to interpret certain things about your function based on what the a value is. So we're going to do this by kind of continuing on what we were working on Friday. Here's the problem that we were finishing up on Friday, and what you should do now is go back and kind of rehash what you've gotten so far, and then continue it on and finish it out in order to answer, giving your prediction for the light intensity at a depth of 25 feet. So to just get us started here, to talk kind of about a plan that we could use, what we want to do is we want to find a way to model and find a way to figure out the pattern that we have in given these points. And the way that we can do that is by finding the average rates of change and see what this pattern is actually doing. And from that point on, we can then try and build a function that could model this data and use that function to predict the light intensity at a depth of 25 feet. So go ahead and give this a try, finish it out. I will have a solution posted in a few seconds, and then we'll move on. Okay. A couple things that I want to talk about. The first is that I'm looking at the average rate of change, and I know that my average rate of change is going to be negative between each of the intervals because my light intensity is decreasing. So it's going to be negative, and I can also see that not only is it negative, but its negative value is getting closer and closer to 0. So if I'm thinking about what this looks like on a graph, the slope is getting less steep and less steep and less steep as I go forward, which means that I could model this with an exponential function whose b value is going to be less than 1, right? Because when I'm constantly raising a number less than 1 and greater than 0 to a higher and higher value, I am getting smaller and smaller values back. So I know that my function is going to have this basic form where my input variable is the depth, and now I'm seeking to find a and b values that would model this data and use that to predict. Now here's where you have a lot of choice. You can use any of these two values to fit your function. You know that when you plug one of these points in to find a or b, you're forcing your function to go through that particular point. So if you use the first two values, you're making sure that your function will go through these 2 points. Notice that I chose the first point and the last point, thinking that if I make sure it goes through the last point, it's going to be more accurate. But I encourage you to do the ones that make sense to you, maybe even try see what it would be if you chose different points and see how that would change your answer. And of course then when I find my value, I plug in 25 and see that I will get about 1.1 lumens. Think about whether that makes sense or not. It seems like it's decreasing and getting closer and closer to a 0 value, so that seems to be what I'm looking for. Alright, so here is the total expenditures, which means amount spent, in billions of dollars in the US for nursing home care. And the first thing I want you to do is look at the data and come up with a question, something that you might want to figure out based on this data. When I look at this data, I notice that I end at 2008. Well, it's currently 2015. So the question that we're going to want to answer is, what would we expect the expenditures to be in 2015? What would you predict for 2015? So go ahead and pause the video, create a plan for yourself about how you're going to make that prediction, and then carry it out. So this is very similar to the previous problem. We want to find the pattern and see if we can think about what type of a function would model this pattern. So to do that, go and find the average rates of change and see what's happening as the function moves forward. If you decide you are able to figure out what type of a function it is, then you can try and create a function using the points. Important to know what you are using for your year here. We might say this is the initial value, so we might say this is year 0, and every year after is the number of years after 1990. So for example, in my function, my input variable, x here, this might be the years after 1990. So my initial value can be found, my initial value would be 53, and that could be found when I plugged in 0. And then to find the value at 95, that would be when I plug in a value of 5. So thinking about when I get to 05, there I'm plugging in 15, that would be my value 15 years after 1990. Go ahead and work through this problem. I'm not going to give you any more hints here. You can do this, and then move forward. We've got a couple more to look at. Alright, so here we're going to start looking at the functions, and based on the parameters, just like we talked about at the beginning, based on the parameters, try and answer some questions. So the number of bacteria in millions in a sample after t hours is given by the function n of t equals 800 times 3/4 to the t. Once again, I want you to think about, if you were given this function and told this, what would be some questions that you might want to answer? So when I think about learning about how numbers of bacteria change, the first thing that I might want to know is, well, how much are in there to begin with? So how many at the beginning? The next thing is that I might want to know how I expect the number of bacteria to change. So the next question that we want to answer is, what is going to happen to the number of bacteria as time goes by? Alright, so pause the video and go ahead and answer those two questions, and then we will talk about them. So first, how many at the start? Well, the start is when the t value that we're inputting, when t is equal to 0. So this would be n of 0, and 800 times 3/4 to the 0. Well, 3/4 to the 0, that's 1. So n of 0, the value at the beginning, is simply going to be 800 million bacteria. So 800 million bacteria. Okay, now what will happen to the number of bacteria as time goes on, or time increases? So here there are a couple of options. Maybe you want to plug in different t values. Start with 0, go to 1, go to 2, go to 3, and see what happens. That's perfectly fine. But how can we tell what will happen? Simply by looking at the function. In particular, looking at the parameters. So notice that t is the exponent. So as t increases, we're going to be multiplying our b value, our b constant, by itself more and more times. Well, what happens when I multiply 3/4 by itself increasing numbers of times? 3/4, for example, to the first power, that's 3/4. 3/4 squared, well, now I'm multiplying the top and the bottom by themselves, so I'm going to have 9/16. 3/4 cubed, I have 27/64. So we can see that the value of 3/4 to the t, this part here, is going to be getting smaller and smaller. I mean, just think about it. 3/4, well, that's, 75%. 27 divided by 64, 27 isn't even half of 64. And so we can see that already just by changing t from 1 to 3, the value has gone from 3/4 to less than 1/2. So the number of bacteria is going to decrease. Okay? The number of bacteria is going to decrease. And we want to be even more specific than that. How is it going to decrease? Think about our exponential functions. When a parameter b is less than 1, it is going to approach 0. So what we can say is that the number of bacteria are going to decrease. And how are they going to decrease? Well, it's getting shallower and shallower. So we can say the number of bacteria are going to decrease by less and less and approach a value of 0. All right, last one for us to look at, and hopefully you'll see that we're getting to some more interesting problems that are more real life oriented. So the functions below describe the value of different investments after t months. Compare the two investments, use precise mathematical reasoning to back up your claims. So we've practiced already today coming up with the types of questions that you want to ask. And whenever you see a situation in real life, you want to make sure that you ask the right questions, because if you don't, then you'll come up with answers to things that you don't actually need to know. So imagine that you are thinking about, making investments, and you want to be able to describe the important pieces of each investment strategy. So looking at each of these functions, go through and describe both of them in the real life context, but use the mathematical reasoning behind it to support your claims. All right. In the comment section, along with your question, I want you to state briefly which investment, V sub 1 or V sub 2, which investment strategy you would want to invest in and why. All right. Have a good weekend. See you guys on Monday.